James Webb Space Telescope is built, it has to be tested rigorously. But the telescope at some point needs to be tested as a whole. Webb, though, is enormous, standing several stories tall. To make sure that the observatory will work in deep space, NASA has to use its biggest thermal vacuum chamber, the one here at the Johnson Space Center in Houston, Texas. Hi, Mary.
Hi.
I understand you can tell us more about what you guys are doing with this chamber.
We embarked on a rather large construction project to get our thermal vacuum chamber ready for the James Webb Space Telescope. This chamber has a lot of history stemming back from Apollo times. The chamber itself was actually built in the 1960s to get ready for the space race.
We see a nice wide angle of this. Can we get a closer view of what's really going on in there?
We can go inside and take a closer look.
Mary, why are you taking us out here?
Well, these are the original liquid nitrogen tanks that we used for the testing of Apollo, and it contains all the liquid nitrogen we need to make the chamber below 300 degrees Fahrenheit.
What are we going to see next?
We're going to look at some of the things we've had to remove from the Apollo testing to get ready for James Webb and go up to the 5th level. Solar lamps were part of testing for the Apollo. The vehicle needed to have a high-intensity heat source on one side at a time. Some of them will be closed off, and some of them will be used to pass in new piping for helium.
The helium is for what?
The helium will supply basically like a big soup can inside of the can of the chamber, which is going to make the chamber cold.
Colder than the 300 degrees below zero that Apollo had to face.
Colder than the nitrogen temperatures we had for Apollo. It'll go below 400 degrees for the James Webb Space Telescope. Here we are at the 5th level entrance to the chamber, and I'll let our lead for test operations tell you what we have to do for the vehicle inside the chamber.
As you can see, there's some work going on here. The scaffolding has just been erected. We're about to get ready to start installing the helium shroud. We have to mask off anything when we're done that could be a crack or what we call a stray light path into the interior of the chamber. Any heat sources, any light sources, those would all affect the proper operation of the telescope.
So we're down on the ground level.
This is it. This is the floor of the chamber. What you're actually standing on now used to be an old Apollo lunar turntable. This part of the floor used to rotate, and that's one of the things that's been changed for James Webb. The mechanism that turned the floor had an oil-based CO. Contamination is a risk for us, so that's been replaced and welded. The floor doesn't turn anymore.
So now you can see how NASA's past is paving the way for NASA's Space Telescope at launch. We'll be seeing forces as high as 20 Gs. That's 20 times greater than the force of gravity that you and I feel just walking around here on Earth. Making sure the various parts of the observatory, like this primary Miry segment behind me, will survive the stresses of launch is a big part of the testing going on here at Ball Aerospace in Boulder, Colorado. So Paul, these vibration tests, how long do you actually vibrate these mirrors?
Oh, it's really only for a few seconds at a time when we vibrate it, but we're mimicking the same loads that it will see while it's in the rocket, while it's launching.
Because the launch doesn't take a long time, right?
No, most of the vibration occurs early in the launch, and then very soon will dissipate.
2, 1, 0.
We're about to hit full level sine sweep on this mirror.
What do you mean sine sweep?
What it does, it starts at very low frequency where you'll see the greatest displacement of the mirror. It'll move the most at the beginning, and then it'll get to higher frequencies. And as it gets to higher frequency, the mirror is moving faster, not moving as far at that point. And so you can actually see the mirror speed up as it goes through the sweep.
So is that kind of like what it will see during launch?
It will cover all the same range, the spectrum of forces, just like on launch.
So how do you know that the mirror passed?
We have 40 accelerometers mounted at different locations, different components on this mirror assembly. So each of those accelerometers is measuring essentially the forces that are being applied at every little component of the mirror. And we're continuously getting feedback from those while it's going through the vibration. By looking at all the different components, if one component were to fracture or experience strain or something, we'd be able to see a difference in the behavior of that component before and after the test.
Now I noticed it's in a plastic casing, kind of like it's in its own clean room, essentially.
And we're already inside a clean tent.
Yeah.
This plastic casing is really there for safety for us. Just because the mirror itself is made of beryllium, If there were to be a fracture or damage to the mirror, that beryllium dust can be toxic. And so it's contained in such a way that if there were any kind of problem, at least we would be safe. But to date, we haven't had any such problem with these mirrors.
Well, thanks so much for giving us a closer look at the vibration testing that's going on here.
Oh, you're very welcome.
This vibration test is just one of the many ways engineers are making sure the James Webb Space Telescope is ready to go when it reaches its destination, 1 million miles from Earth. The mid-infrared instrument, or Miry, on the James Webb Space Telescope is unique in a number of ways. First of all, it looks at a different part of the electromagnetic spectrum than the other instruments do. It looks at mid-infrared frequencies. Second of all, it takes both pictures and spectra. To find out more about the Miry, we have with us the European principal investigator, Gillian Wright. Gillian, it looks at the mid-infrared range of frequencies. What is mid-infrared?
Mid-infrared means we look at longer wavelengths compared to what the other instruments do, which is described as near-infrared. It's better at looking through dust. It's also more sensitive to different colors of objects. Lots of molecules that might indicate life on other planets. Those molecules make spectra in the mid-infrared.
It takes pictures and spectra. Why the two?
Yes, because to do our science, we want to be able to take both pictures and spectra. So I suppose in an ideal world, we'd have had 2 mid-infrared instruments on JWST, but there wasn't space, so we built it into just one instrument that does both things.
And I understand we have a real, honest-to-goodness Miry right here at Rutherford Appleton Laboratory, right?
Yes, we're all really excited because we've just finished putting the flight model of the instrument together and we're about to start testing.
So Gillian, this is the Miry, huh?
Yes, this is the Miry. This is the flight instrument, so we need to be very careful. Miry deliberately has a very modular design so that each module, for example, this box here, can be built and tested by itself before we build it into the rest of the instrument.
Did you build these modules all here?
No, we had different modules built in different parts of Europe, because that way we could use the skills of a lot of different institutes, all of which have very specialist knowledge about certain areas of how to do instruments, and we could bring it all together to create the Miry.
But the Miry is both a spectrometer and an imager.
Yes, that's right. So the spectrometer in this, when it's this way around, the spectrometer sits on the top, but we can turn the instrument over so we can take a look at the imager. The light would come in here from the telescope and it hits the mirror, which turns it and sends it to the middle of the instrument. Most of the light is then sent to the imager so that we can take pictures with the imager, and a very small fraction of the light is sent to the spectrometer for us to do spectroscopy.
Gillian, thanks so much for showing us your Miry.
You're very welcome.
As you can see, the Miry is basically 2 instruments in one, and it will be able to do its job because of the help of international partners. Thanks for joining us from another edition of Behind the Web.